All right. Thanks for having me. And my name is Mahsa. I'm an integration engineer at Offchain Labs. Uh, we are the initial builders of Arbitrum, and now the service providers to the DAO. And it's my pleasure to be here with you today and to talk about the common security vulnerabilities when you develop your smart contracts. So let's dive in. I'm going to share my screen. Awesome. Just want to make sure you guys awesome. Okay, great. All right, let's start. So as I said, we are going to talk about the common smart security vulnerabilities and how you can avoid them. And so yeah, again, my name is Mahsa. I'm an integration engineer, but I also have a PhD degree in information system security. This is my Twitter, Telegram, and website. So please feel free to reach out to me if you have any questions about the talk or if there's anything in the talk that excites you and you want to talk about that with me. All right. But before we talk about the security vulnerabilities themselves, I want to take some time and talk about why security matters because it is really important and it's sometimes overlooked. So when you develop your smart contract, when you start coding and you hit deploy and you put it on a public blockchain, like the Ethereum blockchain, you have to know that your code is immutable, meaning that there's no way you can change your code after you deploy. So if there's any bug in the code or if there's anything that you don't like in your code, it's not like traditional days where software bugs were like patched. Here, it doesn't work like that. So there's no way you can change that. So your code sits there forever and you're not able to change that. And the unfortunate thing here is that these smart contracts, they often have a lot of funds in them. And I have a few of security incidents that we've seen during the past couple of years, just to bring your attention to how a single overlooked vulnerability can lead to a huge loss of funds. So we had a DAO hack in 2016 where around $16 million were lost due to the famous reentrancy bug. In 2017, we had the parity multi-sig wallet. I'm sorry, hack. Sorry. We had the parity multi-sig wallet hack, where the attacker was able to permanently freeze around 150 million of dollars due to an access control bug. And we had the Nomad breach hack in 2022, where around 200 million was drained from the contract because anyone could withdraw the funds without validation from the contract. So, as I said, any single overlooked vulnerabilities can lead to destroying the customer and the system itself. So you have to really be careful about the security. And that's why we want to talk about common security vulnerabilities in smart contract today. All right, so here's the agenda. I'm going to talk about the reentrancy, which is a very famous attack vector in smart contract. We are going to talk about arithmetic overflow and underflow, which are basic, simple math errors that opens the door for attackers to exploit your smart contract. We have access control issues where missing or weak permission checks can lead to a lot of severe attacks. And finally, I'm going to talk about front running and MEV, which is minor extractable value, which is about transaction ordering and censorship of transactions on public blockchains like Ethereum blockchain. Oh yeah, and in each case, we're going to talk about how you can avoid them, of course, so that you can walk away with something useful from this talk. All right, so let's talk about reentrancy first. Reentrancy is when a contract makes an external call before updating its own state. And in this case, if the callee contract is a contract that is malicious and is being controlled by the attacker, it can call back to the victim contract. And because the victim contract hasn't updated its state yet, it's basically working with outdated information. So in that case, it can run, I don't know, like any malicious logic they want. And it can repeat things. And because, as I said, the state isn't updated yet, it can repeat things until it can drain the funds. So the basic assumption here for the victim contract is that it is in the middle of a single operation, whereas the attacker is basically repeating things without the victim contract even knowing. But why it can happen? So what allows the attacker contract to call back into the victim contract and repeat things? And that is where the fallback functions in Solidity come into play. So the fallback functions are special functions in Solidity that they run automatically in some certain cases. And they have some specific features. So they have normally no function name. They can't be called internally, so they're only callable by external contracts. And there could only be one fallback function per contract. And these specific functions, they're called in certain cases, as I said. The first one is a call made into a function that does not exist in the contract. And the second one is when Ether is sent to the contract and there's no call data accompanying it. And there's no receive function that is declared, and if the fallback function in the contract is marked as payable. And don't worry if it is too complicated for you. We're going to see the code example and everything, so hopefully it'll be clear. And this fallback function, when it is payable and it receives ETH without any call data, of course, it gets triggered, and it can contain any logic. This is what the scary part. It can have any logic, and that is where the attacker can insert the malicious code. So I have some example for you, as I said, and don't worry about these codes. They're all in a GitHub repo sitting for you to go ahead and test them. I'll link the repo at the end of the talk. So here's the vulnerable contract. It is a simple contract that lets users to deposit some amount inside the contract, and then they're able to withdraw from the contract. But here's the vulnerable part. So the contract allows the user to call the withdraw function, and what it does is it basically transfers Ether to the message.sender, and then it updates the balance. So what happens here is that the attacker can call this withdraw function. What happens is this victim contract, it sends the attacker contract some ETH, and here the attacker, here's the attacker contract. So what it does is first, it has the constructor to just point to the victim contract, so it knows which contract to target. And then it has the deposit. It is just setting the state. So the attacker deposits some ETH into the victim contract so that their balance here gets updated so that they are able to call the withdrawal. So when it happens, they can. This is where the attack starts. So they call the attack, and what happens is it calls the withdrawal from the vulnerable vault, and because that vulnerable vault sends Ether to the attacker contract before updating the balance, and there's no call data with that, the attacker's fallback function gets triggered. And here, what it does, as I said, they can put any code they want. So what they do is they call the withdraw function again. And because the victim contract hasn't updated the balance yet, the withdraw function gets called, and it goes on, and it continues withdrawing from the vulnerable vault until there's no fund to withdraw from the contract. And this is, I just put a simple visual for you so that it's clear. So what happens is the attacker withdraw from the victim contract. Here, balance never gets updated. And so it sends ETH. The fallback gets triggered because it's receiving ETH without any call data. So, and there's no receive function in the contract. And so when fallback gets triggered, again, it calls the withdrawal. So this loop goes indefinitely until the victim contract gets drained. And that's exactly what happened in the DAO hack in 2016, where the attacker exploited the exact same bug from the contract, and they were able to drain $60 million from the contract. So this is a huge security incident, and reentrancy is something we have to keep thinking about when we are writing our codes. But how we can avoid that now that we talked about the vulnerability and everything. So honestly, avoiding it is so simple. It's a pattern that's called check effect interactions. So first you do some effects, and here that means you have to zero out or decrease the balance first, and then only after you do the whatever you want, like interactions. So here that interaction is sending ether to the attacker, to whatever is calling the withdrawal. And if you want to have an extra layer of security, you can always use the non-entrant modifier from the Open Zeppelin, which basically blocks any nested calls into the same function in the contract. So here the safe contract would be, it's again the same vault, but it's safe, of course. So here in the withdrawal, what the contract does, first it does the effect, so it updates the balance. Here we're setting it to 0, but you can decrease it according to how much the attacker is withdrawing. I keep saying attacker, but the person. And then you update the balance first, and then you do the interaction, whatever it is. Here we're sending ether to the withdrawer. So if they call back to the withdraw function again, their balance gets checked, and because their balance has been updated, they're not able to do this loop again and again. So we're safe against reentrancy. So moving over to the next vulnerability, which is arithmetic overflow or underflow. Here is when you use a number in your code that it basically exceeds the maximum or minimum value that its type can store. And what happens is it causes the value to wrap around instead of going forward or backward and creating the expected result. And this is really, like, it may sound simple too, but it can lead to a lot of high-profile security incident. Like it can reset some counters or some votes, or let's jump in and you'll see what happens. So I brought some example for you because I just thought it's easier to explain like that. Let's take uint8 solidity type as an example. These types can only store integers from 0 to 255. So you want to use it in your code. You have variable x from type uint8, and you set it to 254. It is near the max the type can store, but it's fine. You increment it by 1. It is now 255 maximum, but it is still fine. But if you increment it just one more time, it tries to be 256. That's at least what you're expecting from your code to do. But you have to keep in mind that this type can only store up to 255. So what happens here is that instead of incrementing normally like 54, 55, 56, what happens is your code, because 256 doesn't fit, what it does is it wraps back to the minimum 0. So from there, it starts counting as normal. So instead of 256, your code silently, without even throwing any error, it goes to 0 and it starts incrementing like that. So imagine that you're counting votes, let's say, or you're having some, I don't know, IDs that you want to increment, and all of a sudden your code like goes back to 0. And again, this is without throwing any error or any warning. So this is a really silent error that can happen. And on the flip side, we have the arithmetic underflow. We use the same uint8 example that can store integers from 0 to 255. Here you have variable y. You set it to 1, and you subtract it once. It's 0, close to minimum, still fine. But if you subtract it once more, it tries to be -1. But remember that it can only store up to 0, like minimum is 0. So what happens is it wraps to the maximum 255, and it starts subtracting from there. And again, this happens silently. This is the scary part. So how these arithmetic overflows and underflow behave, it really depends on the compiler version in Solidity, because before 0.8, these errors, they happened, so underflows and overflows wrapped silently without the developer or contract even knowing. But it actually got fixed after 0.8, and now they are protected and they revert by default. But you have to remember that you can still disable this using the unchecked block, and you may use the unchecked block or you may not, but if you do, it saves some gas, because it's basically you're eliminating some other extra opcodes for checking these underflow overflows, but you are disabling the checking by default. So you have to make sure that you're not reintroducing the bug. And this is really dangerous, these kind of errors. And the reason is, as I said, you may have some balance check or limit check in your contract, then by wrapping around, it gets bypassed. And you might have, as I said, some voting or some IDs or something that they're counters and they are reset unexpectedly, and they basically like you don't know that, you don't even get alert. Or in the worst extreme case, there might be some token supply that you can just start minting tokens without the contract even knowing, and or voting power manipulation. So you have to really be careful about these kind of attacks. So here the vulnerable contract, as I said, like here the person wants to withdraw from the contract, and if the person tries to withdraw some amount that is bigger their balance, what happens is this number wraps around to the maximum, and they can basically withdraw a huge number from the contract. And the safe one is this is Solidity, like as I said, when the compiler is bigger than 0.8, this by default is prevented. But here it was not, because the person used the unchecked block, maybe because they wanted to save some gas or anything. All right, moving to the next vulnerability, which is access control issues. So here is the vulnerability is when a contract, it fails to properly set restriction on who can call sensitive functions from the contract from the outside. And if it happens, it basically allows the attacker to take control of your contract, so they can drain funds, they can issue tokens, or in the worst extreme case, they can even destroy the contract. So this attack itself, this was the behind of many high-profile security accidents. So the parity wallet, multi-sig wallet that I talked about at the beginning, I think it was in 2017. That was the reason of this bug, basically. So the attacker was able to call a function that they were not supposed to do that, and they were able to permanently freeze $150 million inside the contract, forever gone. So the common mistakes for the access control is that sometimes developers, they forget to add checks, proper access checks. So here anyone can call admin functions. So the rule of thumb in developing smart contract is that you should never assume only the eligible people in the world are going to call your function. So you have to always think about the access control. Or the other common mistake is that sometimes developer, they use weak checks. So they use transaction.origin instead of message.sender, which can be attacked by some phishing style attacks. Or sometimes developers even hard code addresses in an incorrect way, or basically allow them to be changed without any restrictions. And why it is dangerous, as I said, attackers can take ownership of your contract. They can change some critical parameters, including fees, prices, limits that you don't want to. And in extreme case, funds or tokens can be drained from your contracts. So you have to be careful. So access control is not only about having checks. It's about having the right checks in the right place. And that is how you should set your mind to it. All right, and how to avoid, basically, it's really easy. So you have to just think about that and make sure that you use this in right places. So the first one is you can enforce ownership or roles explicitly using the only owner modifier, which only basically allows the owner of the contract to call those sensitive functions. On top of that, you can use OpenZeppelin's ownable or access control patterns, which basically they only allow the owner of the contract to call the function. So it's basically adding the only owner modifier by default. And as I said, you have to carefully review every function that changes the state or configuration. So for every function, you have to ask yourself, who do you want to be able to call this function? And are you putting this, like, the checks in place for that person to be able to do that? So moving to the final security vulnerability on public blockchains, front-running and minor extractable value. What is front-running? So blockchain was born, I can say, to bring transparency and openness. But this same property of openness, it also opens the door for the new attack vectors that were not were not possible in the previous systems. So when everything is public on a blockchain, we all know that. So when a transaction goes to the mempool, or when you hit send transaction to the network, before it gets into a block or it gets finalized, it can be seen and viewed by anyone. So anyone can see your transaction, and if they're willing to pay a higher gas for their transaction, they're able to front run your transaction, or sometimes they can even flood the network with a lot of high gas transaction and basically censor your transaction. So they can not let your transaction go through in a block that you want. Let's say you have a sensitive transaction, time sensitive transaction that you want to send, so they can basically not let you do that. And that would change the outcome in a way that they want. So why front running matters? It is really important. So as I said, the attackers, the malicious person, they can jump ahead of you, users, if they have trades or bids or some beneficial transactions. And miners, validators, or builders, they can reorder transactions for profit. This is what we call minor extractable value. So they can sort transactions in a way that it would benefit them by inserting their transactions in the middle, for example. And sometimes user may pay more gas to just get the worst execution for you than what you're expecting. And it might benefit them as well. So this is a visual that explains how front running works on an Ethereum blockchain. Let's say we have Alice that wants to buy 100x tokens at the best ask price on a decentralized exchange that sits on the Ethereum blockchain. So Alice sends the transaction, but because everything is public, everything is transparent, Mallory, who's the malicious person, she sees the transaction before it even goes through. So Mallory thinks that she can buy that token herself. So what she does is she sends the exact same transaction as Alice. She just pays more gas with her transaction, and next, like right after, she goes ahead and lists the exact same token, the exact same amount on a higher price on the decentralized exchange. So what happens is the miner would see Mallory's transaction, and they would put that in a block earlier than Alice's transaction. So what happens is Alice is buying 100x tokens, but at a higher price from Mallory. So Mallory is benefiting basically from the price difference here, just because she was able to front run Alice's buy transaction. So how we can avoid front running? It is a very complicated problem. So there are some mitigations proposed, different research and different systems. I listed a few of them here. The first one is confidentiality. So the goal here is to hide sensitive details that the attackers can see. So when you interact with a dApp or smart contract on the Ethereum blockchain, there are several things that you can see on the smart contract. So you can see the code of the application. You can see the current state. You can see the name of the function that is being called. And you can even see the parameters that are being fed into the function. You can see the address of the contract that is being invoked, and you can even see the address, somehow the identity of the sender. So if you want to prevent front running, you can think and decide which of these elements you can hide from the attacker. So the best thing here is to kind of obfuscate or hide your function, the name of the function that is being called, and the parameters that are being fed into the function. So if you can use some cryptography to basically, as I said, obfuscate or encrypt these two when you're sending your transaction, this prevents the attacker from seeing what transaction you're sending. So in our previous case, here, if Alice would have encrypted the function that she called and like the number of tokens or the price or everything, then Mallory was not able to see what is the transaction. So she was not able to front run Alice. And the next mitigation, or how we can avoid front running, is just embrace it. So instead of trying to eliminate front running entirely, just try to accept it as a minor extractable value and try to design your system to manage and monetize it in an ethical way. So Time Boost that went live on Arbitrum 1 is a great example because it monetized MEV and it allows users in the system to use that in an ethical way. So that eliminates the front running risk in the system. So when you're designing your system, you have to think about that if you want to use it or not. And the best fix, which I think is the best fix before you design your system, maybe you can design your system in a way that it just removes the incentives entirely. So this is not easy, and it really depends on the use case. But let's again go back to our example, like decentralized exchange on a blockchain. There, if you can use a call market instead of continuous trading, that would have eliminated front running for like entirely. And the reason is because I'm not going to go through the details, but call markets work differently than continuous trading. So in call market, orders are batched, so timing doesn't matter. So if you can eliminate timing and who, like basically eliminating who was first, then you're basically eliminating half of front running risk in your application. So if you're using call markets rather than continuous trading, there's basically no advantage to acting just before someone else. So there's no front running incentive left in your system. That was it for all the security vulnerabilities. As I said, I put all of those codes, the vulnerable ones and the fixed ones, in here on our Off-Chain Labs repo. So I do encourage you to go ahead, look at the contract, test them, and build them with Foundry and explore them, and make sure that you have all those security concerns in your mind when you're writing your code. So the takeaways from my talk, which I want to go through them briefly, is that security is not a one-time thing. So you have to always think like an attacker when you're writing your code, and you have to keep your code simple, because remember, more complexity extends the attack surface. And don't try to overdo things. So instead of it's like creating complicated libraries which can increase the attack surface, try to use the trusted libraries like OpenZeppelin. And no, just remember that audit is great, but it's not a silver bullet. So there can always be bugs in the contract. So you have to always build with safety and be careful. And we all know that crypto is a very fast moving space. So try to stay updated with knowledge, security concerns, and there could be any day, any zero the vulnerabilities that come to space that we don't know about. So try to stay cautious and updated. And I hope your contracts are all safe. And that concluded my talk. I will be on the Arbitrum Foundation Discord open house channel during the day. I'll try to check in. So if you have any questions, as I said, you can definitely reach out to me on socials, but please feel free to go to Arbitrum Discord and ask your questions there. I'll tune in and make sure to answer. And I hope you enjoy the talk and have a great day.